All right, we're starting. So, wrote some examples on the board last time. I believe we got through A and B, so we're starting from C, and we're going to finish up here and move on to some other stuff. So, yeah, let's actually just jump right into it. So f of x equals x squared minus 1 over x minus 1, if your x is not equal to minus 1, x is not equal to 1, and it's equal to 3, x equals to 1. Someone walk me through how they figured out where this is continuous. Where is that continuous? Yeah.
So it's the same, like the problem, the previous problem, we did the same thing. So it's continuous everywhere but 1. But
Okay, how do you know?
Because the bottom has like you can't have like 1 in the bottom, the denominator. When you substitute f of 1 into the equation, you cannot have 1, but you have every other number.
Yes, but we already know that. I said we're not 1.
So then now you take the limit at x. You take the limit of f of x as it approaches 1.
Okay, so the idea is first you talk about at x equals 1, because that is obviously a point of contention here. That's where we're broken up.
Oh, yeah.
So you want to say, are we continuous at 1? So to be continuous at 1, what do we need?
X is like
What does it mean to be continuous?
just be defined. Yeah.
Continuous doesn't mean defined. What does it mean to be continuous?
On the left and the right.
Yes? That's what it means to be continuous at f equals 1. Continuity always means that equation. What does it mean to be continuous at x equals a? It means that the limit as x approaches a of f of x is f of a. So this needs to work for it to be continuous at 1. Now, does that actually work? Well, f of 1 is what? 3. Now, if I take the limit as x approaches 1 of f of x, what is that? Well, that's the limit as x approaches 1 of x squared minus 1 over x minus 1. And how do we find this?
So you
Simplify. We simplify that. Step 2 of our limit process, and you'll realize that the answer is 2. And so here you realize that this is not equal to f of 1. This means not continuous at 1. Otherwise, we're fine. Again, that's because both of these functions individually, they'll be continuous as long as we're not at 1. Because the limit of this will just be whatever number you're going to plug into that thing at 8. So this means here f of x is continuous on the real line except 1. You know what continuity means? It's an equation. Okay, so in D, pretty much the same thing. Just made a small tweak. I made that 2. So how is this going to change things? What is the answer now? Continuous where?
the limit of f of x.
Okay, so So again, we can say if x is not equal to 1, we're fine. So now we're just checking 1. Right? That's just by inspection, you can check the thing. So if x equals 1, we want to check that the limit as x approaches 1 of f of x is f of 1. F of 1 is defined to be 2. And if we look at the limit as x approaches 1 of f of x, this is the limit as x approaches 1 of x squared minus 1 or x minus 1, which is 2. And so this means f is continuous at x equals 1. And since if x is not equals 1, it's also continuous. This means f is continuous everywhere. Another way to say everywhere, this just basically means minus infinity to infinity. So if you have to put that in interval notation, that's what you write. That's how you write out a problem on like a test or a quiz or something like that. Show me that you're considering all points. You're considering when we're not at 1 versus when we are at 1. Because you have to figure out where do the functions individually behave themselves, as well as how do these functions actually connect when we switch the definition of the function. Because even though the functions individually are fine, if we make a new definition, we risk actually causing a break because the y values won't match up. So you always want to see where the functions themselves are working, as well as where the definitions, if they actually connect to each other. Now, I want you to appreciate what actually happened here. I believe we did x squared minus 1 or x minus 1. Versus this one that we just did, x squared minus 1 or x minus 1, if x is not equal to 1 and it's 3, if x equals to 1, versus f of x what was the difference between these? Well, look at the picture for all of them. You'll start to see that our calculations actually make sense. This one, how do you sketch that graph? We looked at that already. That's just going to be a straight line looking like x plus 1, except it's going to have a hole in it. That occurs at the point x equals 1. And that's the picture. Now, that clearly has a break in it, that has a hole right here. This one looks pretty much the same starting out. That is that one. However, we went to x equals 1 and we artificially filled in a value. Now, this hole is pretty much at the level of 2, but what we did was we filled in a point at 3. So what you actually have happened in that situation is that we still end up with a disruption in the function. I can't draw this without lifting my pencil off the page. I have to stop, go over here, fill it in, and then come back here and continue sketching. Right? So that one isn't continuous everywhere. It's continuous as long as we're not around the point 1. We can just keep drawing. Same thing happened here. In this case, though, what you would notice actually happened. Very similar functions, but why was one continuous and all the others weren't? Is because this one started out with a hole at 1, and that hole was at the level of 2. And what we did was we went in and we filled in the hole at 2. So what we did was we artificially bridged the gap. Now, there are no holes in the function, there are no gaps, no disruptions. I can literally just sketch this without lifting my pencil off the page. So the problem that was there at the beginning, I tried to fix it, but I did a bad job over here. But we finally got it right over here, and that was kind of the difference. So earlier, well, last class, when I mentioned, can we fix it? I was talking about this kind of idea. Is there a way for us to artificially create continuity where there was none before? Because if there is such a way, we would tend to want to do it. So let's look at E. What's the write-up for this one? Okay, how would you actually write that one? Right? This showed up on a test. Determine where this function is continuous, and I gave you that example. What would you write? To not only determine the answer, but to show me that you actually understand, you can reason through the answer, you can logically determine this. Yeah, Robin?
You know, first, f of a equals -2. I mean, f of 1 equals -2. That's where we're discontinuous in the first.
That's the first thing you start writing?
That's
That's the very first thing. You're going to write f of 1 equals -2.
What would you say? Limit of f of, I mean, you would write the equation you gave us. Limit f of a equals f of a. X, limit of x approaches to a of f of a should give you f of a.
Do you need f of x here?
Yeah.
That's what it says. Okay, so you're going to write that down. What else would you write?
And then you would write that limit of, no, then you would start writing f of a is, you would know that f of a is defined. So you could write that, and since you know that the problem
What is f of a?
It's f of -2. I mean, f of, yeah.
Yeah?
I would start out by writing f of -2 is equal to 1, and then the second step I would do is write the limit as x approaches -2 of f of x, and then you get an answer of 1, and then you would say that the limit as x approaches -2 of f of x is equal to is equal to f of -2, so that tells you that it's continuous.
No, not exactly. Yes.
I start with the limit of as x approaches -2. I would factor out the numerator, x plus 2, parentheses x plus 3, x plus 2 cancels out, you get x plus 3. You plug in on -2, you figure out that you get 1.
Okay.
And then I go with the second one, so I go f of -2 equals 1. I both get 1, so therefore my function is continuous at x equals -2.
At x equals -2 specifically, that's what you forgot. Okay, then what?
Anything that takes part.
And then?
And then you write the interval notation, negative infinity, comma infinity. All the negative notation.
Yeah, but how can you make that jump?
But yes, we have it.
Yeah.
Yeah.
The limit? He already did this thing where he found the limit. Now, I know it seems like it's a stickler, and I don't want to really go off on too much of a tangent, but being able to communicate an idea is super important. Don't just write down a bunch of random equations on the board. Structure your thoughts, structure your ideas, make sure that you're saying the correct thing. Basically what I'm going to say is something like the following. If x is not at -2, we're fine. Now, for us that is okay, because that indicates to me that, oh, what you looked at is these functions individually, if we're not at -2, it's just a 1, that's always going to be a thing, that's just a horizontal line, you can always plug in it in, and that will be fine. So you just know individually these things are going to work. So that's what this is indicating. Now, sometimes you might have to justify even this statement, but in Calc 1, I let it slide. For you to just recognize that, oh, everything is fine as long as we're not at this point that is specially referenced in the problem. Now, what I'm writing in green, you don't have to write it out, but I just want you to say what the thought process is here, right? So if we're not at this point that we broke the function up, everything's cool, right? That's just a fraction, that's just a 1. They're always going to be defined continuously. So now what you do is you talk about if x equals -2, you deal with that case separately. So we've considered the case when x is not -2, everything seems to work out. So now we're going to consider the case x equals -2. And so we want to figure out, is it continuous at -2? So we need to check that the limit as x approaches -2 of f of x is equal to f of -2. And now you go, f of -2 is 1. And what you realize is the limit as x approaches -2 of f of x. Well, that's going to be the limit as x approaches -2 of this thing. Because you can't approach this thing. This is literally an isolated point, but this will work for everything around -2, which the limit doesn't care about being at -2 either. So when we're taking the limit, we're going to look at the limit of the top part. So as you mentioned, the way you take this limit, which we've discussed, is you're going to try to factor. And it factors like that. You'd realize you'd be able to cancel that part, and you'd actually be able to plug in x equals -2, and you would get 1, which is equal to the f of -2. So that means the continuity works out for this part as well. And then we can conclude f is continuous everywhere. So just by doing these calculations right here, you can't conclude that it's continuous everywhere. You can only conclude it's continuous at 2, right? So if you just show me this and say it's continuous everywhere, you've not really fully developed the thought. So you kind of want to have these statements that are prefacing how you're going to think about this problem. Okay, I'm going to worry about when it's not at -2 and when it is at -2. This covers all cases. When it's not at -2, everything is fine. These functions are nice. I can plug in whatever I want. They'll continuously go on. There's no gaps, there's no hole, there's no breaks. At -2, there's a potential for problem because we literally changed the definition of the function. It's possible that it's not going to connect. So I zoom in on that specifically, actually did my calculations, and I think, oh, it worked out. So it works at -2, and it works when it's not -2, therefore it works everywhere, right? So there's like a whole argument that you're kind of constructing. You just have these random equations all over the place and not even knowing, trying to just take a stab at writing the right equation down. You want to really understand what you're doing in terms of what you need to actually show to actually solve the problem. Let's look at F. Okay, go. Issues. Start example. What are you going to try? Yeah.
If x is not equal to 0, we're fine.
If x is not equal to 0, we're fine. Right?
Yeah.
Why? Well, you look at the individual functions. Well, what does sine x look like? If you look at y equals sine x, right? It looks like this, it goes on forever. Right? no breaks, no gaps, no hold, everything's cool. I can plug in any number, I can approach any number, no gaps. We're awesome. Look at y equals x. That's just a straight line going through the origin. Also, no gaps, no breaks, we're cool. Individually, these functions are cool. The only issue here is I just did a division, which means I create a potential for division by 0, which is a bad thing. And so, when do I obtain division by 0? Specifically when x is 0. So then I was like, okay, this is a point that I need to deal with separately, right? So you're like, if we're not at 0, everything's awesome. Everyone is working. I'm just going to take whatever number this is outputting, divide by that number. I'm going to get an answer. The limit is going to work. It's going to exist. However, because of the division that we just did, now I have to worry about, am I divided by 0? So that's when I go over here and I check 0 specifically. Okay. Now, if x equals 0, here's what's going to happen. We need to check that the limit as x approaches 0 of f of x actually equals f of 0. Now, f of 0 is undefined. Now, it's enough to stop there. You can just say it's not continuous at 0, but I just want to write something down that's going to help us with this second part of the problem. But the limit as x approaches 0 of f of x is going to be the limit as x approaches 0 of sine x over x, which is 1, right? That's something you should have memorized. Okay, so this thing is not continuous at 0, but the reason that it's not continuous is that the function value itself isn't there. The limit is actually fine, which means if I'm considering this question, can I fix it? Now I know where I should be focusing. I should be focusing at redefining the function at this value. Right? So I can say, I can conclude here f is not continuous at x equals 0. This means that f is continuous on minus infinity to 0, union 0 to infinity. And can we fix? And what would you say? Could you actually fix this? I would say the answer is yes, but how do you actually get it done? Yeah.
We fill in the whole f of 0 and we would make it 1.
Right. Now, how would you express that that's what you're doing? Yeah.
You use a piecewise function.
You create a piecewise function that's going to lie right on top of this function. So you can say we can redefine f to be 1 at x equals 0, yielding so what I'm going to do is I'm going to redefine this function. I'm going to let it do whatever it wants as long as it's not at 0, because that was never a problem before. However, at 0 there was a problem because there was a single point out of place. So what I can do is I can actually fill in that point. I'm going to fill in a point with a very special value. The value that coincides with the limit value, because as long as the limit equals the actual value of the function, this makes it continuous. So what you would be able to include the above is continuous where? Everywhere. Because with this guy, the only problem was with 0, but the actual problem was solvable. What you will notice, this one is a little bit harder to sketch. Looks like there's an outline. This is not a part of the graph, that's just a skeleton. At 1, there is a hole, and then it's like a sine function, and then there's this. Keep oscillating. As we move out to infinity, we're dividing by x, so this guy's going to get closer and closer to 0. And same thing is happening here. As we move out, it's going to get closer and closer to 0 because we keep dividing by a larger and larger number. So that's what it originally looked like, and what I did was, oh, that's a bad point. Now everything works, right? So that's what this actually did. We redefined the function so that the point that was misbehaving, I can actually fix it. Okay? Now this is not something that can always work, so I actually want to make some comments about this. The above indicates that F had a, we call it a special name, removable discontinuity. At x equals 0. So that's the idea of a removable discontinuity. There's a point where the function is discontinuous, but I can actually remove this problem by simply redefining the function at a point. And so if f is continuous except at a finite number of points, we say f has removable discontinuities. Continuities at those points if we can fix f by redefining it at those points. I also want to make a note, this is not always possible. Let's look at some examples. First, let me just create some more space here because I'm tired of being confined to half the blackboard. So we're going to do this, but I just want to take a small detour to talk about this idea because it's actually an important idea. Right? The thing we just did by just seeing where the bad point is and filling it in, you can't always do that. So let's actually look at some examples. Example, f of x equals consider that function. Now what you're going to notice, if you went through and you checked everything, is that function is continuous everywhere except 0. So there's one isolated point where it doesn't work. We can see that easily by sketching the picture. It looks like that at 1 or bigger, so it's a horizontal line 1, and for anything less than 0, not including 0, it is -1. Right? So now, here, what you notice is x equals 0 is the only point of discontinuity. Now, if I were to ask you, could I fix that? Could I redefine this function at x equals 0 to change this without drastically changing the nature of the function itself? No, there's no way, right? Because even though there's one x value that's messing up, there's an infinite number of y coordinates that are messing up. There's no way I can fix all of that by just changing this one x value. This thing even has a definition. But even if I were to redefine it at 0, let's define it to be 0, it's still a problem. Let's define it to be a half, it's still a problem. Let's define it to be minus a half, it's still a problem. You can't just fix this one coordinate and fix the whole function, right? It's not actually going to work out, right? So, numbers. Now one thing you might think is, well, at x equals 0, I could just define it to be a vertical line connecting these two. But that's not a function. So technically it wouldn't be a function if you did that. You create some other kind of object. And for us, we're not worrying about that right now. But we can't just take an isolated point and plug in here and fix this. To actually fix this, I'd have to like shift this entire half of the function up or shift this one down. We'd have to drastically change how the function is behaving. It wouldn't be anything close to what it was before. So when you're in such a situation, you're in a situation where there's a point of discontinuity and you can't actually fix it by just redefining it at that point, you say you have an essential discontinuity. So this is just a point that we cannot fix by just redefining it at that point. We can't make the function continuous by redefining it at the isolated point x equals 0. So this is called an essential continuity. In particular, this one is called a jump discontinuity. Why? Because the discontinuity represents a jump in the function. Just to keep with our tradition of math people not being creative when naming things. Hey, we can remove this discontinuity. What do we call it? Removable discontinuity? Hey, this discontinuity is a jump. What do we call it? Jump discontinuity? That's going to leave us like another function, another example where you can actually do this that's slightly different is something like 1 over x. Again, the only bad point there is x equals 0. However, you can actually fix that. This has an essential discontinuity. At x equals 0, called an infinite discontinuity, because it requires like an infinite jump. Specifically, and we'll talk about this later, a vertical asymptote. We'll talk about that in another section. We'll revisit this much later. Right, so continuity just means we can draw the function without lifting our pencil off the page. There's no breaks, there's no gaps, there's no holes. Sometimes functions will have breaks and gaps and holes, and sometimes you can actually fix them by filling in the holes. And you can create a continuous function while not altering the nature of the function too much. You're literally changing one point out of an infinite number of points. You're not actually doing much damage here. So the new function you can create can be pretty much like the old function, except it's much nicer now. There are no breaks, there are no gaps. However, there are some functions where that kind of idea can't work. And so at that point of discontinuity, we're kind of stuck. And all we have to do is just make sure that whenever we're doing calculus or anything else that might be affected, we can't do it at that point. We just have to avoid that point altogether. So, I believe I mentioned this word last time. So, point of discontinuity is just a point where it's not continuous. Where it's not continuous means that that limit equation doesn't work. The limit as x approaches the point is not equal to the value of the function at that point, which clearly is the case here. And that's not something that can be fixed, because no matter what point I filled in, okay, let it equal 1 at x equals 0. There's still a gap. I can't fix it. Okay, let it equal 5. Okay, still a gap. You can't actually fix it by filling in a point. Let's look at this one. Can this one be fixed where it is discontinuous? There should be one obvious point where it is discontinuous. And that's where the division by 0 would happen. So let's do our usual check. Notice that if x is not 1, we're fine. Right? That just tells me, you kind of look at the function, you size it up, and you realize, yeah, the only potential problem here is at 1 itself, because the top is a quadratic. Those are continuous, they have no breaks, no gaps. X minus 1, y equals x minus 1 is a straight line. Those are continuous, they have no breaks or gaps. Individually, they have no breaks or gaps. What happens is, I created a problem when I did division. Now I have to worry about division by 0. Division by 0 happens at x equals 1. So if we're not equals 1, everything is hunky-dory. At 1, though, there's a potential problem. And it turns out this is a legitimate problem. At x equals 1, f of 1 is, so I'm now considering at f of 1, is undefined. Now that's a problem. This means f is not continuous at 1. This means, to answer the question, f is continuous on, well, the entire real line except 1. So now let's deal with the question, can we fix it? Can we? How do you examine whether or not you can fix the problem? Find the limit. So let's actually find the limit. The limit as x approaches 1 of our function. So here I'm examining the question, can we fix it? Well, the limit as x approaches 1 of our function. How would you try to find that limit? Well, you can't plug in, so you're going to try to simplify. That's step 2. This brings you to factor. Does that factor?
Yes.
What is
X plus 3, x minus 1.
x minus 1? So that actually, would cancel that here. And then if I plug in x equals 1, what do I get? 4. So is this fixable?
Yes.
Sure. All we have to do is redefine the function. what it wants to do otherwise. I don't want to change its behavior, because that function might represent something important to me. I don't want to just pretend the reality isn't there. However, I do want to augment reality a little bit so that the math can deal with all cases. So at 1, the right thing to define this as is 4. And now this is continuous everywhere. Okay, the question is about continuity in general, or how we examine continuity, how we determine if we can fix the discontinuity. So to kind of summarize, continuity is just the idea that a function has no breaks, no gaps, no holes, no disruptions. We can determine that a function does not have this at a certain point by checking an equation. So at the point x where x equals a, if we check the equation, the limit as x approaches a of f of x equals f of a. If that equation works out, it's continuous there. And if that equation works out for all points of the function, we say the function, all points in the domain of the function is continuous in general. So whenever you are faced with a function, what you want to do is you want to examine it in its pieces, make sure that every piece is okay. If it's piecewise, you then also have to examine at the points where the function is broken down, and you're always examining it in terms of that equation, the limit as x approaches a of f of x equals f of a. But you should always state where you're looking and make sure that you've looked everywhere. So when you say it's continuous everywhere, you better make sure that you actually looked everywhere. If you just talk about, oh, at the point 1, and then you say everywhere, that's disingenuous. You didn't actually look everywhere. You only looked at 1. So that's kind of the idea. Every now and then you have a function that misbehaves at a certain point, and you can fix it simply by filling in what's going on at that point. And every now and then you can't actually do that. So, yeah. And this one, if the denominator were, say, x plus 1 instead of minus 1, then that would be non-removable. That would be essential. Because I wouldn't be able to cancel the bad point and get a nice number. So this guy pretty much looks, you're curious about the picture. Looks like x plus 3, except at the point 1. And that point that was missing shows up at 4. And what we did was we filled it in. So now it works. Yeah.
Just because I'm a little confused on the trig function ones, like where it's like finding the limit is continuous, like a trig over a trig, like for example, like sine of like 4x or like tangent.
Okay.
If we have time, we can show
So the idea essentially remains the same. So you just made up a function just now. What do you say sine 4x over tangent
2x plus
2x or something? So you know that this is discontinuous. Hopefully you know. We know this is discontinuous at all points where tangent of 2x equals 0, as well as tan 2x is undefined. So the tangent is particularly problematic because it also has gaps in its definition. So where is tangent actually equal to 0? What points are we hitting here? And what else? There's going to be an infinite number.
Yeah.
So Now you're going to have to find the points. Now this is a situation where we have an infinite number of points to consider here. So tan 2x equals 0. Well, this just means that the sine of 2x equals 0, because tangent is sine over cosine. And this will just mean that your 2x must be equal to, when is sine of x 0? You should know this in general. At n pi, where n is an integer. Sine is 0 at all integer multiples of pi. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, minus 5 pi. Plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. Sine equals 0 at every multiple of pi. So your n is going to be n pi over 2. There's going to be an infinite number of them. So every point like that is going to be a point of discontinuity. Also, tan of 2x is undefined when the denominator cosine 2x equals 0. This means your 2x will be n pi over 2, where n is odd. You should know things like that. Where is cosine equal to 0 in general? Where is sine equal to 0 in general? So cosine is 0 at every odd multiple of pi over 2. So plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, etc. And so this is going to be, your x should be n pi over 4, where n is odd. Now to go by this example, one thing you're going to realize, if you actually worked it all out, is that these guys, where the tangent misbehaves because like there's a literal asymptote, I remember how the tangent graph looks. It has an infinite number of asymptotes, right? And it's doing like this. Right? Those things will happen for this function at these coordinates. Every time your x is a value like this. That's not fixable, right? That's going to be a problem. The sine is no problem. However, when tangent equals 0, that happens at these coordinates, and it will turn out that those guys are fixable. And those guys are going to be, well, the points that you can fill in, right? Because they're not going to be an infinite gap, it's just going to be an isolated point out of place. And how do you know what to fill in? Well, you would take a limit for each of them. Right? So if you can look at pi over 2, you're going to take the limit as x approaches pi over 2 of that. Right? And then you try to get these special trig functions in there. So if you're looking at now, you have to fill in a different thing here, or you can probably do it in general, but you try to do like the sine of 4x over 4x, so you have to multiply by 4x separately. Then you do the tangent of 2x over 2x, so you have to multiply by 2x separately. So you realize that the limit is approaching 2 if you're, say, at 0, which is one of the problems. So, for example, at one point, at the point where x equals 0, you would fill that in to be 2, right? And you kind of have to do that for all of these. So usually for trig functions, they present an issue where they do something infinitely often. It's probably not something that's going to show up in Calc 1 in this context. So usually if I'm asking a question of this nature, I would either not ask you about a trig function where there's an infinite number of problems that you have to deal with, or I'll give you a restriction. I'll say, only look at this function within the window 0 to 2 pi. And there'll only be a few bad points in there for you to check all of them. So usually in Calc 1, it's going to be, you have to only check a few things, like 2 or 3 things. But yeah, essentially the idea is going to be the same anyway. Figure out the points that have potential problems. For this problem, it was all points like this and all points like that. And then you pretty much check the limit for all of them. Check that it's continuous for all of them, and then figure out, can I actually fix it? If there's like an infinite number of points to fix, can't fix it. If there's like one isolated hole, yeah, no problem, just fill in the hole. But you kind of have to do this for everything. Did you see a problem like that on homework or something? 'Cause
Yeah.
I'd have to see the specific problem, because I don't think they would ask it.
But it was like just this, just in general, when dealing with trig, trying to limit it.
Yeah, so the process essentially is no different. It's just that the trig, they have peculiarities that you have to deal with, like they have repetitions, right? So it's like you're doing exactly what I showed you, but you just have to do it a lot more in general. But yeah, no, you're always checking limit as x approaches a of f of x, does that equal f of a for all points that we care about. When it works out, it's continuous. If it doesn't work out, it's not continuous. That does not change if you're approaching a trig function. It's just that you have a lot more points to deal with in general, I would say. But you're still doing the same kind of examination for every point. And yeah, things like this, you need to know all these facts about trig. We'll be doing a good decent amount of trig in this class, but like for Calc 2, that's when you're going to really need to know your trig. We'll do a topic called polar coordinates, where if you don't know your trig, you're going to be in trouble. Okay. That was a long enough detour. Let's just move on. What was the next thing I wanted to talk about? Oh, yes. Here's an important kind of problem. It shows up on finals a lot. So I actually want to make sure that we know how to do it. So we're actually going to jump into 2 more examples. So important as in for the final. So remember, I'm not writing your final, someone else will be writing your final. And I might, even if I was writing it, I probably would put a problem like this on it anyway, because I guess it's important in general. It's important for all tests and finals. It's a very common problem type to show up. It's when they give you a function, but they leave some parts of the function as unknowns, and you have to find the unknowns that will make it continuous. So here it is, determine A and B that would make f of x continuous everywhere, or show no such values exist. So here's the one of them. So let's say I gave you a function f of x equals a triple piecewise function. It's 2 sine x. And I think I put a problem similar to this on the last quiz you got on Monday. It was in the bonus section. It's equal to 3a at 0. And it's equal to 4b cosine x when they're greater than 0. B. You'll see things like that. I want to make sure you know how to deal with these kinds of problems. But again, once you're asked about continuity, you're still going to be basing your plan of attack on that, around that same equation. Where does the limit as x approaches a of the function equal to f of a? Just give you some time to copy that down. We'll do one at a time. Maybe I'll ask for some audience input here. How would you approach this problem, do you think? Or what is the first kind of thing you're going to look at? Yeah?
You want to set so that equal to each other at
Why?
so that you could find a possible value for A, and then use the value for A, and then set the second function and the third one equal to each other.
You're going to set this equal to each other. And then do what with that? Okay, that's one equation, two unknowns. What is happening? Yeah.
So like the way I would think about it is like, I would think that the limit of as x approaches 0 for 2 sine x over x should equal the value of 3a for that part to be continuous.
Okay.
And then try to figure out what it should be.
Okay. Again, what's the framework here? How are you looking at it? So maybe I should write these steps down. Faced with a continuity problem, first thing you want to do, identify potential problem points. First thought you have, where is this going to be fine? Where is it not going to be fine, potentially? First thing you think of, every time. Yeah.
So when x does not equal 0, we're fine.
First sentence. Why? You're going to look at each function individually. We already sort of looked at sine x over x, but just again, sine x, continuous, no problem. X, continuous, no problem. The only problem is created when I do the division. Then 0 becomes a problem. 3a, a is going to be a constant, so that's just a horizontal line, no problem. Here, 4b times cosine x, again, no problem. Individually, these guys all work fine. 0 is a problem created here. In addition to that, 0 is literally a point where I break the function up around it, right? So at 0, it's different from when it's to the right of 0, and it's different to the left of 0. So there are 3 phases here. And in order to be continuous, the 3 phases have to connect to each other, right? So that I can draw without losing my pencil off the page. All of that goes into me concluding, you know, at x equals 0 is the only potential problem here. If we're not at 0, we're fine, right? It's the first thing you want to do. Identify where you're fine, identify where the potential problems are. X equals 0 is the only potential problem here. Maybe I should write that down. That's the first thing, okay? You just want to look at the functions globally as a whole, what's going on, assess the environment, make sure, what are the pieces that I have to be paying attention to, right? That's the first thing. Don't just start jumping in, writing down equations, and you're not even knowing exactly what you're looking at, what you're looking for, and if you're even addressing all the problems there. First, identify all the problems. Oh, there's a hole over here, there's an asymptote over here, otherwise everything is fine, so I just need to focus on these 3 things. First thing you want to do, right? That's how you go. Right? Sometimes you go to a problem, you don't just jump in and start doing stuff. No, figure out what's going on first, right? like in a global sense. That's in general for mathematics though, by the way. You always want to think globally before you think locally. And that comes down to when you're solving problems, you're trying to figure out how to solve a problem, that's how you always go. Think globally, and then start getting more specific. Now it turns out when you're actually calculating a problem, you tend to go the other way out, like what PEMDAS would tell you, you start from the inside and work your way out. But you have to actually to figure out, how would I get to the inside? That's the first thing. And so that's a common problem. So there are times when you see something like, I don't know, I'm just making something up. So I'm also teaching pre-calc this semester, so I'll be giving my class equations like that to solve. And that's going to confuse a lot of them, and it's because they don't recognize it's just a quadratic equation, even though there's a sine function there, right? So you look at that, the first thing you try to look for is global. In general, what's the pattern here? What are the potential issues? You're going to notice that, oh, there's something with a square, there's the thing again, and then there's a number without the thing. It's a quadratic. So the first thing you want to see is a quadratic. They, of course, will focus on the sines. They'll start jumping in there and like, well, the sine is bouncing up, I don't know what to do, right? That's not how you approach a problem. Look globally. What is going on as a whole? Figure out where the potential issues are, and then you move in and start dealing specifically, right? So the sine x does not come into play until like the last leg of the problem, right? But a lot of people would focus on that first. No, globally, it's a quadratic, right? That's like a general rule of thumb. Pretty much every time you want to figure out how to solve a mathematical problem, that's how you're going to start. Look on the general state of things. Where are the potential issues? Then move in and deal with them, right? So that's always the first thing you're going to do. You don't just start writing down an equation. Where do you need to be setting up the equations, right? The important equation is the limit as x approaches a of f of x equals f of a. In order to even start doing that, you need to know what is A. What is the point I'm going to be doing this at, right? That's always the first consideration. Where are the points A that I need to be checking? Right? Don't just start, oh, let's set this equal to that. Let's plug this in here. No, figure out where you should be looking first, okay? Now, so x equals, if we're not at 0, we're fine. So 0 itself is the only potential problem. So I'm going to zoom in with that. So, and of course, remember the important equation. Once it is talking about continuity, you should be thinking of one equation more than everything else. So now we're going to focus at x equals 0. I determined that if we're not at 0, everything is cool. What is going on at 0 now? Now I have to check, we need to check what? We need to check that the limit as x approaches 0 of the function, does it actually equal the value of the function? Or I need to make sure that I can find values that is going to force this to work. So let's start with the right side. That should be simple. What is f of 0? Here, f of 0 is 3a. Okay, now what about the limit as x approaches 0 of f of x? There are two different ones. The function changes when I'm on the left side of 0 versus the right side of 0. So what I need to make sure is that these two actually match up. So now I realize that there are two things to consider over here. There's the limit as x is approaching 0 from the left of the function, and then there's the limit as x is approaching 0 from the right side of the function. and you would just know that we need these to be equal. And we also need them to be equal to f of 0. Right, so you're thinking through the problem. What do I need to make sure it happens? Right? Now, let's focus on one at a time, like I said. So this one is going to come down to what? When I'm looking at the left, what is my function? 2 sine x over x. When x is less than 0, that's the definition. Less than 0 means I'm on the left side of 0. What's that limit? 2. So that limit is actually 2. If I'm on the right side of 0, what's going on? Well, this is the limit as x approaches 0 of 4b cosine x. And as x approaches 0, what is that limit? 4b. So ultimately, by going through just checking the equation, you now have a bunch of things that you know need to happen. For continuity, we need 3a to be equal to 2. We also need that 2 to be equal to 4e. Right? I need these guys to be equal, so that means that 2 must be equal to 4b. And I need to make sure that the limit coincides with that value, which, if the limit is supposed to be 2, then I need 2 also equal to 3a. Well, that just means your a must be 2/3, and your b must be 1/2. You understand the process, like what I do? So I'm faced with a problem. Hey, this thing is, I'll get you. I'm faced with a problem. Hey, where is this thing continuous? For which values? What do I do? Assess globally. Okay, where are the potential issues? Once I identify them, I go one at a time and I deal with them. How do I deal with them? Well, with the continuity equation. That's what I'm trying to figure out. So I need to check, does the limit as x approaches a of f of x equals f of a for the points x equals a that I identified in the first step, right? Sometimes, of course, you might have to break up, you have to pay attention to how things are defined, so you might go to the left and the right, but for the limit to work, you need these two to match up, and for continuity, you need the limit and that to match up. Now that's going to allow you to set up a bunch of equations where you're going to solve the values, if it's this kind of problem. Yeah, Michael, what was your? They were just constants, they were unknowns, it was given, right? So it's assumed that they're just numbers, and you had to determine what they had to be to make the function continuous. So they're just numbers. So I know to make this continuous the way it's defined, what values do I have to plug in here and here to make it work? And it turns out the values are 2/3 and 1/2. So if you plug in 2/3 here and 1/2 there, the function now becomes something that's continuous everywhere. Because that would mean that at 0, the limit equals the value of the function, and if we're not at 0, everything is fine. So all the functions work individually, and they all connect to the same thing. So there's no disruption. Let's try the other one. Maybe after going through the other one, you'll realize if you really understand. Maybe I'll create more space. So again, the goal, a and b are constants. We need to find the values that they should be. That's so that when I plug in these values, the function as described will be continuous everywhere. Okay, go. What's the first thing I'm going to figure out? Potential problems. What are the potential problems here? So I'm going to figure out, well, potential problems. On one hand, these are going to be easy because it's going to be what the function is broken up around. Notice that at x equals 1, there's a break that we put in. And at x equals 4, there's a break that we put in. So x equals 1, x equals 4. Any other potential problems here? What kind of function is this? Quadratic. Any problems? No, those are continuous everywhere. What kind of function would this be?
Linear.
It's linear, it's a straight line. Any potential problems? No. What kind of function is this? It's a radical. Any potential problems?
0, 1, negative.
Yeah, there's a potential problem here, right? So, what do we need for this to work? Right, you need 2x plus 1 to be greater than or equal to 0. That means your x must be greater than or equal to minus 1/2. And here we said x is greater than 4, which means it's already greater than minus 1/2. So this is okay because x greater than 4 here. So there was a potential problem, but it's we don't actually have to worry about it because the problem occurs where at a point where that's not the definition, right? So it only takes on this value when x is greater than 4, and for 4 or bigger, this works, right? So really the only potential problems are the 1 and the 4. So what we're going to do is we're going to deal with them separately. At x equals 1. Okay, what do we want to do at x equals 1? Right, we need the limit as x approaches 1 of the function to be f of 1. Now, f of 1, do we know what that is? That's a plus b, right? So I find where is x equals 1? Here, right? That's where it's equal to 1. That's the definition. At 1, plug in 1, I get a plus b. So that is the value of the function. Like, okay, so I need to make sure that the limit equals a plus b, whatever that is. So that's the first thing I'm going to check. The second thing I'm going to check is the limit as x approaches 1 of f of x. And what is that going to be? Huh? Well, that depends, because around 1, something different happens on the left side and the right side, right? So to consider this fully, I need to consider two things. What if I'm on the left of 1? And what if I'm on the right of 1? Right? Because it actually branches off. On the left of 1, I'm this. On the right of 1, I'm that. So if I'm on the left, the thing being considered is x minus 1 squared. What's the limit as x approaches 1 from the left of that? 0. On the right, the function is ax plus b. Well, that's a plus b, right? So this means at x equals 1, we need that a plus b must be 0, right? Because for continuity to work, all of these guys have to be the same value. I know specifically what the value of one of them is, which means that automatically all the others have to be that value. So a plus b, 0, and a plus b must all give the same value. In other words, I need this equation to work. Now that's one equation and two unknowns, so that's not enough information right now. So what I would do is move on to the other one. Hopefully I pick up some helpful information. At x equals 4, I need the limit as x approaches 4 of f of x to equal f of 4. Now, start out by identifying the value. What is f of 4? 4a plus b. Okay, now look at the limit part of this equation. What is the limit as x approaches 4 of f of x?
You have to examine from the left hand.
Yeah, you need the left and the right examination again, right? So when we're coming from the left, what function is in play? The ax plus b. When I'm coming from the right, what function is in play? The radical. Now, this one is going to be 4a plus b. This one is going to be what? 3. So ultimately now I can determine this. At x equals 4, we need 4a plus b to be equal to 3. That is, there are two things that you need to actually make this thing work out. A plus b must be equal to 0, and 4a plus b must be equal to 3. This is a system of linear equations. We can solve this for a and b. How would you do this? Subtract what from what?
The second equation. The first equation was the
This is
second.
equation 1, that's equation 2. It doesn't really matter, but let's say I'm going to take 2 from 1. Let's say I'm going to take 2 minus 1. That is going to give me 4a minus a, b minus b, 0, 3 minus 0, 3. This means that my a must be 1. And that's actually a part of the answer. And this immediately means that b equals minus 1, because 1 plus b. So that's the answer. For this function to work out that I erased, we need the a to be the value 1 and the b to be the value minus 1. Any questions on that? Yeah, so that's an important kind of function, very common kind of function to show up on a calculus exam. I'll put a problem like that on the first test, and in all likelihood, a problem like that will be on the final. What can I talk about in 10 minutes? Let's talk about one-sided continuity. And these are just things that we know, definition. We should just know what they are. We say f is continuous from the left at x equals a if the limit as x approaches a from the left of the x equals a. So here we considering a one-sided limit for the continuity equation, and we say f is continuous on the right at x equals a if the right-sided limit for the continuity equation works out. So these are just some new definitions that we want to put in so that we can talk about some functions that we want to, that are simple, that we can understand, but that they don't deal well with the continuity equations, even though we kind of want them to deal with the continuity equations. It's kind of like when we're talking about limits, and it's like, the limit does not exist, but you could tell what the value of the function was doing, so you invented the one-sided limit. So I can say, okay, on the left it's doing this, I know exactly what's going on the right side it's doing this, I know exactly what's going on. It's just that they don't connect. So I can't talk about a limit, but from one side at a time, I can fully assess the situation. In the same way, in terms of continuity, sometimes from one side at a time, you can fully assess the situation, and you want to be able to ignore another side. And so, here's a very important example why this definition would work out, why we care about this definition. Consider, say, y equals the square root of x. Now, here is a function that does that, but none of the values over here are applicable, right? You can't plug them into the square root of x. But here's the thing, though. I would want to call that function continuous for every value on its domain. Because really, from the moment the function starts, it never stops. There's no disruption. But technically, I can't say it's continuous at 0. Why? Because the limit at 0 does not exist from a technical standpoint. Why? Because you can't approach it from the left. Right? You can only actually approach it from one side. But the truth is, only one side is actually applicable. So, here what you'll notice is that the limit as x approaches 0 of radical x actually does not exist. But if you look at the limit as x approaches 0 from the right of radical x, the answer is 0. And for this function, I'm calling on this specific example. We'd like to not care about the left anyway. Okay? Because why would we care about the left? We're only doing real calculus, as in not complex analysis. We're doing real analysis calculus. So only the real numbers actually work. So the left side wouldn't be something I want to consider anyway. So at the point 0, I would only actually consider this from the right. So since So for a nice function like radical x, a very simple function that we'd like to be able to talk about, we'd like to be able to call it continuous because there really is no disruption. It's just that it doesn't go everywhere. And y equals ln x would be a similar kind of situation. Looked at this a while ago. Again, well, that's not continuous at 0 in either case. But the left side isn't something that we'd be worried about anyway, right? So especially if we're talking about the limit as x is approaching 0, it's always kind of understood that we're talking about from the right side. And so we don't, sometimes we just don't say it. But we can't just ignore stuff. We have to come up with a whole other definition that says it's okay that we ignore it because we're only considering a one-sided continuity in this case. Okay. So we allow one-sided continuity suffice for continuity in general. When only one side is applicable. And with this, we can talk about I'm going to introduce some people here. Most of them you've been familiar with, but now we're just going to introduce the official guest of the remainder of your real calculus journey. We call them the elementary continuous functions. So these are the basic building blocks. These are like, if this was chemistry, these would be the atoms in our periodic table. We're essentially not going to be caring about functions that aren't here in this list or come from some combination of things that are in this list. We're going to be using these guys to build up everything. The following are continuous on their domain. They're considered continuous on their domain. One, the polynomials. They're a class of functions on their own. They can be lines, parabolas, cubics, etc. Nth degree polynomials in general. Two, the trig functions. Sin x, cosine x, tangent x, all that stuff. 3, radicals. Now the only reason we can put these on the list is because I just defined one-sided continuity. These guys are considered continuous on their domain. Or rational functions. These are like polynomials when we divide one polynomial by another. Like x plus 2 divided by x plus 1, that would live here. As long as these are continuous on their domain, so that means as long as you're not at the point that makes the denominator 0, the function will actually be continuous. 5. Exponential functions. This includes the function y equals e to the x, which is the most important function in all of mathematics. E, the last one is logarithms, which now we know are the inverse functions for exponential functions. These are the elementary continuous functions. There are only 6 of them. At any given time, we are either going to be talking about one of these functions or a combination of these functions. So an unofficial 7th one is the algebraic functions. Which it's really a bad name because at higher level mathematics, algebraic actually means something different. But for us, it just means a combination of the previous 6. Via arithmetic or composition. So there are times when you would hear me or someone else say, oh, this has no answer, like we can't actually make a computation. And what someone tends to mean when they say that, if they're not talking about it can be infinity or something like that, it just means I cannot write down the answer in terms of these 6 functions. Right? So you'll have situations like that, and we'll talk about that. That'll come towards the last leg of the course. I'll start talking about that. There's no way to actually write down an answer for this thing in terms of the elementary functions. So these are all the functions we'll be studying and combinations of them, and they're the important list of guys to remember. These are our periodic, this is our periodic table. You should know each of these functions very well, how they behave, what their domain is, where they break down. Get to know them very well. I will see you guys next